Hello, everybody. In this talk, we show the stability and the logarithmic decay of the solution to Hadamard type autonomous mass nonlinear fractional differential equation. This is a joint work with my PhD student Changping Li. The outline of this report is organized as follows. We introduce Hadamard fractional calculus, then we introduce some definitions about the Hadamard fractional differential equation. Then we show the stability and the logarithmic decay of the Hadamard fractional differential equation with two kinds of derivative. Then we give a brief summary. Hadamard fractional calculus was born in 1892. It has members Hadamard integral, Hadamard derivative, capital Hadamard derivative. There are some existing works. This is the early work by Kielbasa. Then there are books by three authors. And also this paper is in the edited book by Dumitru and Noor. And there is a paper by Dumitru and his co-authors. Then this is Ma and me, and this is the I and my peer student Sawa. Okay. Now we show the Hadamard fractional integral for a given function with order alpha. Alpha is always positive number. We can define like this. Here this is the 1 over gamma alpha. This is integral. This is a curl with a logarithmic function. Here is dt d tau over tau. Okay. Here we require t is bigger than a, I is a positive number. Okay. From the above definition, we can define its derivative like this here for alpha bigger than 1 minus 2, n minus 1, but less than n. And this is delta, and delta n is defined like this. So the Hadamard derivative of the function ft is equal to 1 over gamma n minus alpha. This is delta n, okay? And this is the curl. This is the curl. And here there is tau, okay? If we exchange the order of the delta operation and the integral, we get the capital Hadamard derivative like this. Okay. Now we show the null spaces of these two kinds of derivative operator. For the Hadamard derivative operator is null space is given like this. Here is for this the power is alpha minus 1, alpha minus n is negative. Okay. For the capital derivative, because the capital Hadamard derivative is null space is given like this. 1 is log t over a. These two kinds of definitions are not equivalent with each other, but they has a relationship between, but there is a relationship between them given by this equation. Okay, this initial value. Now we have the definitions of the Hadamard derivative and the capital Hadamard derivative. How to go will pose the conditions for such kinds of different equation. We just take a simple example of alpha in this interval. This is the Hadamard derivative. This is the integral initial value condition. Now this all equivalent will give like this. Okay, here is the SA, but here is the gamma 2 minus alpha. Okay, or we can give a initial condition as 0 equals 0, but t0 is far from the initial time a. So it seems that Hadamard derivative is not suitable for applications in applied science and engineering due to the non-local definition conditions you see here. Okay. But for the capital Hadamard case, we can go the initial value condition like the classical integer order different equation like this. Okay. So capital Hadamard derivative seems more suitable for application in applied science and engineering. Now we give some definitions about these two kinds of equation. Here and after, we always first introduce capital Hadamard case, then Hadamard case. So this is capital Hadamard differential equation. If ft is equal to 0 for all t bigger than or equal to a is a positive number, we can call x equal is an equilibrium or the equation. This is the capital Hadamard Fractional differential system. For the Hadamard case, the origin x equals 0 is called an equilibrium. If ft0 equal to 0 for all t bigger than a is a positive number. In this case, the starting point a generally can be not reachable. The zero solution to capital Hadamard case, sense of capital Hadamard case equilibrium can be moved to the origin. Okay, so we can define the zero solution to the capital Hadamard case with this order is said to be stable if for all initial value conditions there exists an epsilon because 0 such that this holds for all t. Okay, asymptotically stable if this holds. This is just the nearby of stability for such kind of equation. The zero solution, the Hadamard case, with Hadamard system 1.5 with order alpha is irresistible is said to be stable if for all initial value conditions there exists epsilon positive. A tilde bigger than a such that this holds for all t bigger than or equal to tilde a bigger than 0. Asymptotically stable if this holds. Okay. For autonomous nonlinear differential systems, capital case, capital equation, capital Hadamard equation, and Hadamard equation. The origin is an equilibrium for capital Hadamard systems if or only f0 is equal to 0 for all t. Okay, and is an equilibrium of Hadamard system 1.7 if and only if f0 equals 0 for all t. Here is t bigger than a. Here t is bigger than or equal to a. Okay. Assume that the orange is an unique equilibrium of capital Hadamard system or Hadamard system, and that all eigenvalues of the linearized matrix satisfies this no zero eigenvalue, and the arguments of all eigenvalues in absolute value is not equal to pi alpha over 2. Then we call the orange a hyperbolic equilibrium of system 1.6 or 1.7. Now, that we W as subsets of Rn, suppose that Fs and Gy are continuous vector fields of defined on V and W respectively, and that the generate flows phi Tf from V to V and phi Tg from W to W. If there is this homeomorphism H from V to W such that H phi Tf equal to phi Tg H for X in this region and this, okay. The Fs and the Gy are locally topologically equivalent. If the above relation holds in a whole space way, then they are globally topologically equivalent. Now we show the stability and the logarithmic decay for the capital Hadamard case first. For the following autonomous nonlinear difference system, this is the capital Hadamard derivative. We always suppose that Fs satisfies the Lipschitz condition, which guarantees the uniqueness of the solution. So such equation has only one solution. The following is the linearized theorem, first version of the Hadamard theorem, or the autonomous nonlinear fractional difference system with capital Hadamard derivative. If the origin is a hyperbolic equilibrium of the capital Hadamard system 2.9, the vector field Fs is topologically equivalent with its linearization vector field F prime 0x in the neighborhood of U0 of the origin. So these are local equivalence, okay? Now we show the stability theorem. For the capital Hadamard system 2.9, if all eigenvalues of the Jacobian matrix L prime 0 satisfies this, then the zero solution of capital Hadamard system is locally asymptotically stable with logarithmic decay. That is, the components of the state decay towards 0 like this. This is the decay rate. Okay. If at least one eigenvalue of the Jacobian matrix satisfies this, then the zero solution of Hadamard system is unstable. Now there is a remark. If the Jacobi matrix has a critical eigenvalues is a zero, there's a zero eigenvalue, or arguments of the eigenvalues in absolute value equal to pi alpha over 2, which means that the zero solution is not a hyperbolic equilibrium, then we cannot judge whether or not the zero solution is locally stable or unstable. We need the high order approximation of the effects near the equilibrium. Now we show the Hadamard case. We consider the following autonomous nonlinear differential system with Hadamard derivative. Now we have the following linearization theorem. If the orange is the hyperbolic equilibrium of Hadamard system 2.2, then the vector field FS is locally topological equivalent with the linearization vector factor L prime 0x in the neighborhood U0 of the orange. Okay, we must state that this is a local topological equivalence. Since we use the linearizations. Okay. Now we show the stability theorem for the Hadamard system 2.2. If all eigenvalues of the Jacobi matrix L' 0 satisfies this, are all arguments of all eigenvalues in absolute value bigger than pi alpha over 2, then the zero solution of Hadamard system 2.2 is locally symplectically stable with a logarithmic decay. That is, the components of the state decay towards zero like this. Compared to capital Hadamard case, it has a different decay. For the capital Hadamard case, here is the minus alpha, but here is the minus alpha minus 1. Okay. If at least one eigenvalue of the Jacobi matrix satisfies this, then the zero solution of the Hadamard system 2.2 is unstable. We have the same remark for the capital case, for the capital system 2.2. Okay, we need the if the zero solution is not a hyperbolic equilibrium, then we cannot judge whether or not the zero solution is locally stable or unstable. Okay. Now we give a summary for the talk in this verbal conference. Decay towards an equilibrium. Okay. Decay towards an equilibrium. If yes, okay. For the ordinary differential equation, it is exponential decay. Okay. But for capital, for the ordinary differential equation with capital derivative, it's algebraic decay. We can ask the readers refer to the Marion's paper in 1996, another paper, and the linearization for this case can find this paper. For the capital Hadamard, for the ordinary differential equation with capital Hadamard derivative or Hadamard derivative, it is the logarithmic decay, the result was reported in this paper. Okay. Now, thank organizers for invitation, and thank you all for participation. Thank you very much.